Okay, here's a classic statics problem. Let's say you have a mass that's suspended by a cable hanging from the end of a bar with a certain mass, and the whole thing is suspended by another cable that connects at the end down here. What I want to caution you about is it's easy to fall into the trap of thinking that if I have this cable running along here and down to here, that the tension in this part of the cable is the same as the tension in this part of the cable. Actually, excuse me, that's not the way it works. If you look closely at this point right here, the two cables are different. This one supports M, the big M, and this one supports the whole thing, the bar and the mass M. So let's say that we have a situation where the mass, big M, is equal to 50 kilograms. And let's say also that the mass of the bar, let's call that little m, is equal to 10 kilograms. And let's say that the length of the bar, L, we'll call it, not that we really need it, but let's put it on there anyway. The length of the bar is 2 meters. And let's say that the angle, theta, is equal to 60 degrees. And what else? Let's say that the acceleration due to gravity, g, is equal to 9.81 meters per second squared. So what we want to find is the tension in this cable, T we'll call it. We'll call this one the tension. I'll draw a vector here to indicate the tension T in the cable. We want to know what that is. We also want to know what the horizontal and the vertical forces are on the hinge that connect this whole apparatus to the wall here. So I'll write that as, I'll make a picture of that. Here's the vertical component of the force, and here is the horizontal component of the force, like this. And they may not be accurately drawn, but we'll find that out once we solve the problem. So in addition to the tension in the cable, we want the vertical component of the force. We don't know what that is. We want to know the horizontal component of the force. We want to know what that is. And let's see, one other thing. Let's say that we want to know what the angle that the resultant force against the wall makes. And we'll say that is something like this. This angle here, alpha. We also want to know alpha. All right. How do we set this up? Let's start by indicating the mass of the bar, and the effect of gravity on it means that we have a force acting in this direction associated with the mass of the bar, and let's just call that m, little m times g. The force of gravity associated with the big mass is just big M times g, like that. So the first thing we want to do is look at the force balance equation. By force balance, I mean the downward forces. If we want to find out what the tension in the cable is, we need to look at what the downward forces are and what the upward forces are to see how they balance. So let's write an equation for force balance. The upward forces acting on this system here, which consists of the bar and the big mass M, well, the force upward due to the hinge on the wall, F sub V, plus the vertical component of the tension, which is just, as you can see from the picture here, that's T sine theta. This is T sine theta. So F sub V times t sine theta are the upward forces. That's the only ones we have. This one, which acts at this point, and this one. And those have to be equal to the downward forces, which are just little mg plus big mg. And we could write that as g times big M plus little m. The next thing we want to do is look at the torque balance. This bar is exerting a torque about this point, and this mass is exerting a torque about this point, and the cable, which is attached at the end, is exerting a torque about this point. These are the clockwise torques, little mg times this length, and big mg times this length are the clockwise torques. And the counterclockwise torque, there's only one if I calculated about this point right here, which is just t sine theta acting at this distance right here. So I can write the torque equation like this. Let's say the clockwise torques, which are mg times L over 2 plus big mg times L, has to be equal to the counterclockwise torque, which is t sine theta times L. And you'll notice earlier I said you don't really need the length, so you notice L appears in each of these terms, so I can just cross that out. I can divide both sides by L, and then if I divide this side by sine theta and divide the other side by sine theta, then I have t. So t is equal to g times little m over 2 plus big M, and all of this is divided by sine theta. So all I have to do is plug in the numbers that I'm given to find what the answer is. And I'm going to plug those in. This is 9.81. And little m was, what did I say? Little m was 10 kilograms. So that's 10 kilograms divided by 2 plus big M, which is 50. And all of that is divided by the sine of 60 degrees. And let's see, let me get my calculator and we'll put that in there. So, okay, 10 divided by 2 is 5 plus 50 is 55. So 55 times, I've already stored G in one of my memory locations, times 9.81 is equal to whatever the numerator turns out to be, that, and I'm going to divide that by the sine of 60 degrees, and I get 623.02. So that's approximately equal to 623.02 newtons. And that's the first thing that I want to find out. Very easy. I didn't even need my force balance equation. Okay, so for the rest of the problem, I want to find the vertical component of the force and the horizontal component. Well, the horizontal component I can get easily because here it is. T times cosine theta points this way. The horizontal component of the force that the wall exerts at the hinge here is the same, has to be equal to T cosine theta. So I can just write down F horizontal is equal to T times cosine theta. So that's equal to 623.02 times cosine of 60 degrees, and that works out to be approximately, well, let's see, here's my 623 that I left in there, times the cosine of 60 degrees, and that's equal to 311.51 approximately, and I'm going to store that in one of my memory locations. 311.51 newtons. And that's what the horizontal component of the force is. All right, the vertical component I can get from this equation, this equation right up here. The vertical component, let me make sure that we can see it up here. In fact, I'll just write it right here. I'll solve this equation up here for FV. And this one means then that FV is equal to G times big M plus little m minus T sine theta. And I'm going to plug the numbers into that equation. I'm going to have to move it out of the way here so you can see it. So FV is equal to G, which is 9.81, times big M, which is 50, plus little m, which is 10, minus T, which is 623.02, times the sine of 60 degrees. And that works out to be, put it in the calculator here, 60 times G minus 623.02 times the sine of 60 degrees, and that's equal to 49.05 newtons. That's the vertical component of the force, which is quite a bit smaller than the horizontal component. And finally, I want to find the angle alpha. So alpha is equal to arctangent of the ratio of the vertical component to the horizontal component, which is FV over FH, and that's equal to the angle whose tangent is 49.05, 49.05 divided by 311.51, and that works out to be approximately, well, let's see, 49.05 divided by 311.5 equals that, and the inverse tangent of that is equal to 8.95 degrees. And that's what I wanted to find, and that's how you do it. Just be careful when you do these problems that you realize that this cable here is different from this one. It's not the same tension, because you could be tempted to try to solve for T immediately and have it be just equal to the weight of big mass M. So be careful about that.